Today we're going to continue our conversation about estimating parameters and determining sample sizes. So we'll be focusing on the population mean today. The main key concept that we're going to have today is going to be using the sample mean to make an inference about the value of the corresponding population mean. And again, there will be three main concepts that we have. The first is the super straightforward one, the point estimate. The idea that the sample mean that we have is the best point estimate or single value estimate of the population mean. What this means for us is if we're given a sample mean and we want to find the population mean, that sample mean is the point estimate of the population mean, our best point estimate. So we won't be doing a whole lot of focusing on that. What we'll focus on instead is the idea of building a confidence interval. So we're going to use sample data to construct and interpret a confidence interval estimate of the true value of the population mean. And then we'll be talking about how we can find the sample size necessary to estimate a population mean. So let's jump into this confidence interval thing. Our variables that we'll have involved here are mu, our population mean, n, the number of sample values, x bar, our sample mean, e for our margin of error, and s for our sample standard deviation. So when we want to determine a confidence interval for estimating the population mean, when we don't know the population standard deviation, that's important. We're going to first talk about when we don't know our population standard deviation. If we do know our population standard deviation, we're going to do something slightly different, which we'll talk about later on in this video. So we have two requirements we need to check when we don't know our population standard deviation. The first is that our sample is a simple random sample. And the second is that either or both of these conditions are met. The first is that the population is normally distributed, or n is greater than 30. Hopefully this rings a bell, being similar to the central limit theorem. That's exactly what's happening here. Similar or exactly the same requirements of that. So in order to construct a confidence interval, we need a margin of error, just like we did when we were talking about the population proportion. So the margin of error is going to be determined by taking t sub alpha divided by 2. We'll talk a little bit more about that t sub alpha divided by 2 in a minute. And then we're going to multiply that times our sample standard deviation s divided by the square root of our sample size n. And we'll be using df equals n minus 1. All right. We'll also talk about what that df thing means in just a minute as well. So when we're looking for a 95% confidence interval or a 0.95 confidence interval, this again corresponds to an alpha value of 0.05. All right. Our confidence interval level or our confidence level is 1 minus alpha. So all of that unchanged from when we were talking about population proportions. So let's talk about what this t sub alpha divided by 2 is. Well, it's called a critical value. It's a critical t value that's separating an area of alpha divided by 2 in the right tail of the student t distribution. Again, we'll come back to that in a minute. All right. Degrees of freedom is something that we're going to need to deal with. Degrees of freedom, we write it as df for short, and it is the number of degrees of freedom used when finding our critical value. We'll talk a little bit more about what that is also a little bit later. So first things first, our round off rule. When we get to the point where we have an answer, if we're using original data sets to find our values, we're going to round to one more decimal place than our original data, just like our round off rule was when we were finding the sample mean to begin with. And if we instead are using summary statistics, so we're using the sample size and our X bar and S, we're going to round to the same number of decimal places as those things have, because they already have gone through this round off rule. So we want our confidence interval to follow the same round off rules that our mean follows, basically. So what is this student t-distribution thing? So if a population has a normal distribution, then the distribution of this t-statistic thing here, where t is equal to X bar, or sample mean, minus our population mean, divided by S divided by the square root of n, right? This is the student t-distribution for all samples of size n, and the student t-distribution is commonly referred to as just a t-distribution. So degrees of freedom. We need these to find our t sub alpha divided by 2 value. And in general, what this is, for a collection of data, it's the number of sample values that can vary after certain restrictions have been put into place. Right? So for us, our values that can vary, if we have a certain sample mean that we're looking at, all but the last value of our sample numbers can be whatever we want them to be. And then that last value, we can choose it so that the sample mean turns out to be what it's supposed to be. That's why our degrees of freedom is going to be n minus 1. So it lets all but one of our sample values vary and be whatever they want. And then we'll use that one that cannot vary to make our sample mean be what it needs to be. So you can remember why it is, or you can remember that our degrees of freedom, when we're trying to estimate the population mean with our sample mean, is going to be n minus 1. So finding our critical value t sub alpha divided by 2. Technology can help us out here, or what we'll be using is table A3. Table A3 has only selected values in it, and only selected values of degrees of freedom, but we'll be sticking to examples where we can use it, or things that allow us to be close to it. So we can use the closest value when we don't match up exactly, and we can also kind of interpolate between two values in the table if we need to as well. So what this t-distribution looks like. Basically, it's symmetric about 0, the same way the normal distribution is. So in this picture here, we have a green graph. That's the standard normal distribution. And then you'll notice that we have two different t-distributions here. One with 12 as our sample size and one with 3. Now you'll notice the one with 12 is closer to the actual normal distribution, and the one with 3 is a little bit further from it. Something to note, the peak of the bell of these is a little bit lower for the t-distributions, and the height of the tails is a little bit higher. So what this means is it still has this symmetric shape, still has a mean of 0, but the variability is greater. All right, and as we have smaller sample sizes, the variability is even greater. So some key things, again, symmetric about 0, t equals 0, and its variation, its standard deviation is going to be greater than 1. And again, as n gets larger, it gets closer and closer to the normal distribution. All right, so let's look at a procedure for constructing our confidence interval for our population mean. First, we're going to verify our two requirements are satisfied, that it was a simple random sample and that the population is normally distributed or our sample size is greater than 30. So since we're in the case where we don't know our population standard deviation, we'll be using n-1 degrees of freedom, and we'll be using our t-distribution table to find a critical value t sub alpha divided by 2 that corresponds to our desired confidence level. So first things we need to do is evaluate the margin of error using E equals t sub alpha divided by 2 times our sample standard deviation divided by the square root of n. And once we've found that, then we'll do the same thing we did with our population proportion. So we're going to take our sample mean and subtract our error, our margin of error, and that's going to be less than our population mean. And the value that's going to be the one that's greater than our population mean will be our sample mean plus our margin of error. So we can report our confidence interval that way, or we can use our sample mean plus or minus our margin of error, or we can use interval notation to denote it. So if we have our original set of data values again, our round off rule, what will round these values that we get to will be 1 decimal place more than our original data set. Or if we're using these summary statistics, we're going to round them to the same number of decimal places that's used for the sample mean. All right, let's take a look at an example. So we're going to find the critical value t sub alpha divided by 2 corresponding to a 95% confidence interval, given that the sample size or sample has n equals 15 elements in it. So since n equals 15, we're going to use the degrees of freedom of n minus 1, so 15 minus 1, which is 14. And we'll have 95% confidence interval, which means alpha, it's a typo, it shouldn't be sigma, it's alpha, is 0.05. So there's an area of 0.025, alpha divided by 2, in each of the two tails of the t-distribution, as we've shown here. So we're not going to use technology for what we're doing, but we'll be using the table. So using table A3 to find our critical value, we're going to use the column with the 0.05 for our alpha in two tails. All right, so there's a column that says area in two tails, and we'll be looking at 0.05. All right. Or we can use the same column with 0.025 for the area in one tail. Either way, it's going to give us the same answer. And then we're going to look for the number of degrees of freedom of 14. And when we find that, we're going to find t sub alpha divided by 2, or t sub 0.025, it's going to be equal to 2.145. All right. Now, this table, table A3, is going to be posted on the course Moodle page, so don't worry about needing to find it somewhere else. It'll be there for you, so you'll be able to take a look at it and follow along with what's going on here. All right, so finding a point estimate and margin of error from a confidence interval. We can do this the same way that we did when we were trying to find our point estimate for our proportion from our confidence interval we were given. So if we're given a confidence interval, instead of being given stuff to find a confidence interval, and we're asked to find that point estimate, we're going to take our upper confidence limit and our lower confidence limit, and we're going to add them together and divide by 2. We're taking the mean of those two values, and in doing so, we'll be finding a point estimate for our sample mean. And if we need to find our margin of error, what we do is we take the distance between our upper confidence limit and our lower confidence limit by subtracting them, and we divide it by 2 to find what half that distance is. And that'll be our margin of error. So now let's talk about finding a sample size required to estimate a population mean. Right? This is what we're going to be working with. Again, we have the same variables that we've had along the way, We have our population mean, our population standard deviation, our sample mean, our desired margin of error, and we're going to be back to working with z-scores. All right, so this is with our standard normal distribution. So our requirement to be able to find this sample size is that the sample must be a simple random sample. As long as we have that, we can do this. So our sample size that we require is going to be found by taking z sub alpha divided by 2 times our population standard deviation divided by our margin of error that we desire, and then squaring all of that. And again, if it's not a whole number, we're always going to round up and say we need the next larger whole number. That way we always have a sufficient amount and not like just barely not enough, right? So that's the case where we know our population standard deviation, which we haven't really been dealing with that situation for the entirety of this lesson so far. So what happens when we're in the case where we were with all of the stuff we've talked about so far, when we don't know what our population standard deviation is? Well, what we can do is we can take our data and we can estimate the standard deviation using the range rule of thumb by taking the range from our sample data and dividing it by 4. And that gives us an estimate of our population standard deviation that we can use. We can also choose to use our sample standard deviation as an estimate of our population standard deviation, that point estimate idea. So we'll use S in place of sigma. All right, the larger our sample is, the better that estimate will be if we're doing that. And finally, we can use prior information or prior results of some earlier study, and we can estimate the value of our population standard deviation based on that. So let's take a look at an example of this. If we want to know the IQ score for the population of statistics students, how many statistics students do we need to randomly select for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? So since we want a 95% confidence interval, we have alpha is 0.05. So when we're looking for z sub alpha divided by 2, we get 1.96. Now, because we want the sample mean to be within 3 IQ points of the population mean, our margin of error that we desire is 3. So E is going to be 3. And since we know from previous IQ things that the IQ of the entire population of human beings has a standard deviation of 15, we can estimate that the population of statistics students has a standard deviation of 15 as well. So that's where our sigma equals 15 is coming from. So we'll take n, and we will take our z sub alpha divided by 2, multiply it times our estimated population standard deviation, divide it by our desired margin of error, and square that. And in doing so, we get 96.04. And since we always round up when we have anything that's not a whole number, we need a sample size of 97. So the interpretation of this is that among the thousands of statistics students, we need to obtain a simple random sample of at least 97 of their IQ scores. With a simple random sample of only 97 students, we will be 95% confident that the sample mean is within 3 IQ points of the true population mean. So now let's talk for a little bit about what do we do when we do know the population standard deviation? Because sometimes we do know the population standard deviation even if we don't know the population mean. When this is the case, instead of using the t-distribution, we can use the standard normal distribution. So to find our margin of error, we'll take z sub alpha divided by 2 and multiply it times sigma divided by the square root of n. So here's an example of this playing out. So we have 15 birth weights given to us. So n is 15. We can find the mean of those birth weights. It is 30.9. And we can construct a 95% confidence interval of the mean birth weights for all girls by assuming that sigma is known to be 2.9. So we know that the standard deviation of birth weight for all girls is 2.9, so we're going to use that. So we go through our requirement check. It's a simple random sample. Because our sample size n equals 15, the requirement that the population is normally distributed or the sample size is greater than 30, it has to be normally distributed. So we need to look for normality. So this is the normal quantile plot of our data. Again, you don't have to be able to make one of these plots. You need to be able to interpret one. And remember, it's normal if it looks linear, like there's nothing else weird going on and the data is kind of close to a line. So we have that happening here. So we have normal data. So we have our requirements. So now to find a 95% confidence level, or with a 95% confidence level, we're going to take alpha to be 0.05, typo there, don't get caught up in that. So 0.05 is alpha because that's 1 minus 0.95. So we're going to get that z sub alpha divided by 2 is z sub alpha, z sub 0.025, which is 1.96. And remember our standard deviation that we're assuming is 2.9, and our sample size n is 15. So we'll find the value of the margin of error by taking z sub alpha divided by 2 times that population standard deviation divided by the square root of the sample size. And when we do that, we get 1.46760. So now what we'll do is we'll take our sample mean, 30.9, and we'll subtract our margin of error, 1.46760, from it. And when we round that to a single decimal place, as we would be doing because our original data had no decimal places, so we need to round to one more than that. So we get a lower limit for our confidence interval of 29.4, and we then will take our margin of error and add it to our sample mean to determine the upper limit for our confidence interval of 30.4. Really quick, remember that we just did, it's when we know the population standard deviation. It's a whole lot more realistic and more common that we won't know what the population standard deviation is, in which case we'll have to use the previous method, and so go back to the example before that. And just to wrap it up, remember when our population standard deviation is not known, but it's a normally distributed population, or our sample size is greater than 30, we can use the t-distribution. When our population standard deviation is known and it's normally distributed, or our sample size is greater than 30, we can use the z-distribution. And if the population is not normally distributed and our sample size is less than or equal to 30, there's a process called bootstrapping that we can go through. We are not going to do that. So we're going to be sticking to situations where we can do this because our sample size is greater than 30 or it's normally distributed. And whenever we run into a situation where it's not normally distributed and n is less than or equal to 30, we're going to look at that and say, sorry, don't know how to do that. We're not doing it.